Hey folks, so as Chris said, my name is Galen. I work for Chef Software, and today I'm talking about system accidents, understanding common failures. So real quick, who am I? Why am I talking about things? I've been with Chef for about 6 years now, which is at least 2 lifetimes in the DevOps world. I'm based in San Diego, so not too far away. And I'm currently the lead compliance and security architect for Chef. So I go around to our customers talking specifically about our compliance and security product, how it fits into the kind of InfoSec or DevSecOps kind of planning and structures. Before that, I was a solutions and customer architect, so both on the pre and post-sales side for Chef. I am a global traveler. I have not yet been to any places that have coronavirus when I was there. So, but on the other hand, you probably still don't want to shake my hand thanks to the current epidemic, soon-to-be pandemic. So what we're talking about today are systems, and a couple components I want to get off the bat here are some rules about systems that we're talking about. First is that systems are inherently complex. We're talking about typically things that are large scale, a lot of complexity, multi-location, things like that. Systems are often tightly coupled, and what I mean by that is to say that they depend upon each other in tightly coupled, tight interactions. So if one thing goes down, other things may fail as a result of that particular failure. They can have common mode components. A common mode component is a thing that multiple systems rely upon, right? So like Splunk being a centralized logger is a thing that multiple things might rely upon, or say like AWS or Azure or VMware, all those things would also be considered common mode. And a system is inclusive of the technical, mechanical, and human components. A system does not exclude the people in part of it, does not exclude the mechanical components or any of the technical software or any of those other things as well. So we're talking about a system, we're talking about the entirety of the system here. And a system has a potential for catastrophic failure, which is to say that it can fail in a catastrophic way in kind of a all-encompassing way in terms of this talk. So when we say system accident, what are we actually talking about? And the definition we're using today is just the unanticipated interaction of multiple failures. So we're saying not a single thing failed, not a couple things failed in different places, and that caused us a kind of a big incident, big concern, but multiple failures interacted in a way that we didn't anticipate, that we didn't foresee, that we didn't have any ability to plan for, and as a result of that, the system failed in a catastrophic fashion. And when we're talking about system accidents, the easiest way to start is in the industrial system space. So a great example is 3 Mile Island. This is many years ago. And there's a lot of pieces to this system that are important to think about when we think about what happened with the 3 Mile Island accident. The first is the complexity. A nuclear reactor is inherently complex, right? There's a lot of transformational processes that happen inside of the reactor. A lot of things have to go right in a particular order, in a particular fashion, at a particular time. They have to be tightly regulated. If they're not, interactions can happen out of control, things like that. Coupling. One of the key components in 3 Mile Island is that the safety systems are actually tightly coupled to the reactor operation. One of the things that happened in 3 Mile Island is that the primary safety system is in fact also the primary power generation system of the steam turbines. And when that system goes offline, power stops, but then we have to think about backup safety systems, right? The system is not single use, it is used in multiple components. Common mode. A pressure release valve in the 3 Mile Island incident was stuck open, resulting in the secondary systems pumping in water into the reactor to be less effective. So what happened is a small amount of water leaked from one of the systems in the nuclear reactor. About a cupful of water is the estimate. In that process, it triggered some automatic processes to safety shut down the system. One of the components that exists is a pressure relief valve, and that valve became stuck open while they're pumping more water into the system and trying to figure out what's going on, why is the pressure not coming back online, why is the system not responding the way they want it to do. And then the safety system failure, a critical backup water system was inoperable due to valves being closed. The rule, the steadfast, hard rule in 3 Mile Island is that that safety system can never be offline during a normal operation. However, that system was physically offline, physically padlocked, closed during normal operation. Shouldn't have happened. Nobody can tell who it happened, right? Oftentimes when we look back at 3 Mile Island and things like this, we see operator failure being the kind of the component here. But what I think is interesting is that it's not operator failure in a single moment. It's the system itself is complex enough and tightly coupled enough and has enough common components that When these things go wrong in conjunction with each other, the safety system was offline because the valves were closed, the pressure relief valve became stuck open, there was another component where one of the lights was out on a dashboard to show that the pressure relief valve hadn't closed. All these things together result in the actual failure of radioactive leak in 3 Mile Island and the subsequent fallout from that. So you're like, cool, this is DevOps days, man. Like, I'm not a nuclear reactor operator. Like, why the hell do I care about this? All right, so let's talk about Google Cloud. Let's talk about a thing that we can care a lot more about, a lot more recent. This is incident number 19009 from Google Cloud, and they call this kind of the Catch-22 incident. What happened here is there was a misconfiguration applied to the Google network services to the multiple regions. It was supposed to apply to only a few subset of their overall network, but in the process, it went and applied to everything. In the process of applying this particular network update, it literally has to take down parts of the network stack to make this happen. And a lot of things started to happen wrong very quickly for Google. First is that Google operates with a lot of complexity, a lot of resiliency and redundancy for defense in depth. They also have a little bit looser of a couple. When you make a configuration change to Google Cloud, or when the Google Cloud network team makes this change, there's actually a window of time where the system operates before applying that change, giving operators a time to catch their particular failure or particular issue and respond to it. In this particular case, that window was not enough time. So what resulted in happening is that the core network infrastructure dropped offline for the majority of Google's regions and zones. And then, in order for Google to make the fix change, two things occurred that were really problematic. One is that Google had no clear backup of what the settings were before the change, so they had nothing that they could roll back to, no way to know what the previous state was. And secondly, Google network team was now relying upon the same very, very clogged network pipes that everybody else was relying upon. So not only did they have a problem of not knowing the previous state, of not knowing what the complexity of the system was, but they also relied upon the same network infrastructure that was already oversaturated because everything else was offline, continuing to exacerbate their problem before they could get the systems back up online. All right, DevOps days, Google Cloud, it's great, but like I'm really not a cloud infrastructure guy. I don't have that stuff. So what about something smaller? I'm just a middling, place. Maybe I'm a university, maybe I'm a bank. First off, you're not middling. You're great, right? Let's be clear. Come on, you're all great people here. We're all here to solve problems. But there's a lot of things that can go wrong inside even smaller organizations. So this is a pretty common one from System Center Configuration Manager. I have seen a couple of these smaller things in my own life and previous jobs. There's a lot of ways in which this goes wrong. But basically, what's happened publicly to at least two companies is this. An operating system reimage is scheduled for a set of systems, typically for the desktop systems, but is accidentally applied to every system in the fleet. This is one of the things that happens in System Center when you're selecting your set of systems. If you misclick or kind of otherwise do things and you have greater than necessary permissions, you can potentially literally reimage your entire fleet of systems directly as you go forward. Now, the problem here is that as soon as this automation gets kicked off, there is no callback. There's no way to tell the system, nope, stop that, don't do that. It just goes and tells the system everything to go make this happen. So both Emery University and Combank in Australia both had full-on outages because every system started the wipe process. Now, this includes Active Directory controllers, this includes the file servers, everything, right? And so as a result, a couple things really kind of happen. One, the key piece here is the complexity. The tool used is complex and is limited really by the operator's experience, right? Both times what we call this is be operator error. My argument is pretty straightforward that the system complexity should not be limited by the operator's experience. That's not operator error, that's system error. The second is the coupling. Once the order is given, there's no way to kind of piece it out or roll it back or otherwise kind of deal with it. It's just given, and that is the entirety of what we get to work with. And then the process, in this particular case, the system definitions are built manually in a UI and applied through the same UI. There's no ability to check and review changes short of implementing a user or human process, right? Having an experienced admin look over the shoulder of a junior admin before they make a change. And the last example I want to talk about is Maersk Shipping. Has anybody seen this Maersk, not Petra example yet? See a few hands. There's a really, really great Wired article about this that goes in some serious depth about what happened. But the basic structure is that NotPetya virus got out in Ukraine. And in Ukraine, there's a Maersk office. And one of their accountants had a particular piece of accounting software, which is what NotPetya targeted in terms of its attack vector into systems, and got onto a Maersk computer in the Ukraine, and then subsequently spread through their entire network. Maersk at the time had a flat network, totally flat across the entirety of their infrastructure. All their desktop systems had access to production, vice versa, etc. NotPetya, if you're not familiar with the virus, is a ransomware virus, except it's not actually ransomware. It's one of the fake ones that even if you pay, you're still not getting your data back. Maersk employees were running around offices trying to unplug computers from walls, power things down before things could get lost. They end up convening a team with Deloitte in London to sit down and figure out how do we rebuild the network? How do we rebuild the entire infrastructure? And they've got offsite backups for just about everything. And they're really getting there, and they go, what about Active Directory? And everybody looks around and goes, we had 250 Active Directory controllers spread across some 60 countries. Nobody ever assumed that the entirety of Active Directory could go down all at the exact same time. So they had to figure out, with this complexity in the environment, how do we rebuild Active Directory? It's the brains of the control systems, all this stuff. Turns out a single server in an African country was offline due to a network outage at the time of the attack. And they had a single Active Directory server that existed that they could pull from. They literally flew someone there, flew the hard drives from that system directly to London to literally put them into a rack to rebuild Active Directory from the lone remaining backup of their entire fleet. So core issue, there's a couple things here, right? Like, look, the initial attack vector is really just this virus that goes across the network. It's a ransomware. But there's a lot of things that go wrong to make this a true system accident. A, the complexity of the network design, or in this case, the lack of complexity, followed by the complexity of your backup and remediation structure. Common mode, Active Directory is a thing that is relied upon by most, if not all, enterprise processes, right? If no full backup of Active Directory results in a particular issue here. And then the process, they didn't have a test of a full system failure. Again, nobody assumed it was possible for all of Active Directory to go down all at once, right? It was not part of their test or their failure plan. All right, so I go through these examples to start thinking about what are the questions we should be asking about in our system design about why these things matter, right? About complexity, about coupling, about common mode components, and about people and process. And these first questions are just about complexity. Are your interactions documented? Is the way the system operates known on paper in some fashion somewhere, right? If the interaction between development and operations is that John hands it over to Sally, is that documented? Do we know what that looks like, right? Do we have an idea of what that interaction is? The interaction itself, is it an automatic interaction or manual? Is it an actual human-to-human passover? Or is it, hey, I put the code in this location, you go grab it, your automation grabs it, whatever it is, right? How do we kind of think about those things? We think about systems themselves. Are they scalable, right? If we need to add more systems or remove systems from the fleet, can we do so in an automatic and resilient and quick fashion? And one of the key questions here is, what complexity is irreducible? One of the things we think about a lot, or we hear a lot in terms of vendor pitches and people talking about things like, oh, I'm reducing or removing complexity. The things we do as systems are inherently complex. We have multiple pieces that interact with each other. They interact with each other regularly. As we go more microservice and API oriented, those interactions become more and more complex. We need to make sure we make the right design decisions, but understand that some of the complexity we have just has to get managed, not reduced. So what does that complexity look like? What is the kind of minimum bar that we can think about and work with? Then how do you handle your dependencies? If you depend upon AWS, how do you handle that? Or if you're depending upon OpenSSL, or pick the recent CVE of the day, right? What do those dependency chains look like? How do we know what they look like? How do we kind of see and visualize this? And complexity is really about making sure that the things are visible to us so we know what the complexity load is. And so the key questions we have here, the key kind of answers to these things we typically see is one path to production in terms of your interactions. Code goes into source code management. Source code management gets picked up by CI and CD systems that gets deployed out to production. Humans can have actions to do inside of those processes, but typically they are not actually moving the code from one folder to another. The number of customers we still see where some of their production applications are literally developer logging into a box and hand copying files that rely upon your services or the other services that you're building have a clear understanding of how to make that stuff happen. Scalable systems, often dealing with microservices, chunking things out into smaller pieces. And again, this gets into what complexity is irreducible. Which things can we manage, which things can't we manage as we go forward. In the dependencies and things, we need to version our artifacts. We need to know what version of everything is running in production, right? What version of the image we're operating with, what image of the software we're working with, what image of our configuration management. All those things need to be codified so we know what a complete system looks like. Then we need to codify those interactions. This is where CI, CD, and DevOps really come into play. In terms of coupling, again, these questions are, I didn't make this a Q&A one, my bad. What services rely upon other services? How do we test those interactions? What happens if a service can't reach a necessary service? Does it go down? Does it wait? What are these kinds of things we look for? Are we relying upon the product or the service or on a specific system? Does the application code say, hey, go reach Dagobah at this address? Or does it say, hey, go find the database server? Or in this case, a Jedi training system, right? Figure out what that system looks like and make sure we build these things in. So the first thing is buffering. Having some structure where a system and a subsystem has a time to recover from an event, right? If the thing it's talking to goes down, should it fail automatically? Maybe that's the right thing, but we should make a conscious decision about that. And if it isn't the right thing, then let's figure out how we make sure that the system can queue things up and idle and otherwise kind of figure itself out before calling itself a failure, or not calling itself a failure, no, it's not a failure. Calling that there is a failure occurring and raising an incident and making things happen. Resilience. We want to build for resiliency, not redundancy. Things like service discovery, auto-scaling, things that allow us to make automatic decisions about bringing systems online or otherwise kind of building through them is really important. Chaos engineering is a key component of building and testing resiliency. I'll talk about that a little bit more in just a minute. And again, linearity, a singular flow of changes to the system. Again, I call this one path to production, right? There's a single way that a change happens to the system, regardless of what the change is. I don't care if it's a small bug fix. I don't care if it's a feature request. I don't care if it's a security update. I don't care if it's a patching of an OpenSSL library. Fundamentally, if we have a single path to production, we can see what that path is and we can codify it and we can work with it. And observability. We need to be able to monitor and see the state of the system. One of the things that happened in 3 Mile Island is that a light was out that prevented them from having an accurate view of the current state of the system. You need to have that accurate view to be able to handle an incident, to be able to make things happen, to be able to solve your problems. Then common mode. This is another one that's really important. What core components do all of our systems rely upon? So, and start thinking like, if you're on a data center, you're relying upon your data center power. If you're in the cloud, you're relying upon AWS, Azure, GCP, maybe you're on Oracle, I don't know. Figure those things out. And then one of the key components we think about when we're talking to our customers in particular is, what components do you rely upon that you don't own? You don't own Amazon. You don't own Google. And when they go down, there is a potential impact to your business. We've had many conversations that are very clear of, we go, hey, look, what happens if Amazon goes down? And they go, you know what? We have SLAs with them. We have pieces with that. We're willing to take that risk to our business. But it's a conscious decision. There are other times we go ask that question, what happens if Amazon goes down? They're like, we would be offline and the company would go under. Like, well, then that's not an acceptable risk decision, right? You have to make a decision about what that looks like. And then how tightly coupled are things to each other? Are you tied to Amazon directly? Are you using all the Amazon services? Great. If that's the right thing for you, that's the right thing. But understand you're making a coupling decision, that if those things go down, your systems will go down as well. So identify your risk, identify your common mode components, perform risk assessments on those, understand what the cost of the business is if those things go down. SLAs are great, There are pieces in there that they give you back the money you spent with them, but do they cover you for the loss of your business in the process? Failure untested is failure unknown. If you're not paying attention to the chaos engineering stuff, there's a couple of vendors who are showing up in the space. It's looking really interesting. There's a lot of good stuff coming out of that. Really highly recommend you look at chaos engineering on your systems. If you're not familiar with the concept is one of my favorite pieces of all time to come out of Netflix. And it's basically, Netflix figured out that they were having system resiliency problems, and they figured out the way to solve it was to say, hey, look, we're going to write some automation that literally takes out part of our application stack during production, during the day, from like 10 a.m. to 3 p.m. Why? Because that's when our people are online and awake. And also Netflix kind of gets to cheat and be like, well, 10 to 3, hopefully it's the lowest part of their day compared to evenings and early mornings and whatnot due to time zones. And so they literally take out parts of their system automatically, regularly, and the system has to be resilient to that failure. So if you remember years ago, Netflix was a bit unstable. It's because they were just unleashing this, and they were finding a lot of bugs, a lot of pieces in their system that weren't quite resilient. As a result, Netflix is now one of the most resilient things in the world. Their Simian Army is the automation stuff, is pieces that they've open sourced, and other people have built on top of it or built their own components as well. Again, this is about testing failure. If you don't test it, you don't know what you don't know. Again, I want to reiterate resiliency over redundancy. Redundancy is all about building multiple systems so we have redundant systems in case one fails. But again, a redundant system, if it doesn't know how to find new ones, can't recover on its own. A resilient system will find a new system when it comes online and recover. These are some of the components we see between microservices, API-oriented architectures, things like that. And agnostic systems, loosely coupled, easily replaceable, right? The thing your application should be looking for is an endpoint at a spot that performs in a certain way. Not, I'm looking for a particular server at this IP address with this port, with this username, with this password. Most of that stuff should come in at configuration, and as the system gets updated, those things will get updated as well. And the last kind of real piece to talk through here is that people and process. Small, resilient, agile teams work. One of the things that's been super fascinating to me as I've gone through this space is that the pieces that we're building on top of Agile and Lean are really born out of the same processes and the same beliefs that the Toyota Production System espouses, and they apply to basically every single field. So the first example I have there is called Team of Teams. It's a book by General Stanley McChrystal talking about how they solved Al-Qaeda in Iraq as a joint special forces operation. When he took over, he found that the various special forces, while really good at their individual jobs, were really bad at getting together and making things happen as a full team. So the SEALs would make a raid, bring in a bunch of intel, and then it would sit in a locker for about 3 months before the CIA would even look at it. And by that time, of course, the terrorist cell had moved on. They had scattered all their pieces, and by the time that intel got looked at, it was no longer actionable. And so what he took over was made a joint forces, and they got to this point where they would do what they called a knock-on raid. So overnight, they would raid on a particular terrorist leader. They would go find that person, pull intel from that, analyze the intel into the morning, and then when somebody else showed up, then keep surveillance on the location they had just raided. And then when somebody shows up in the morning, they would tail that person through the air, figure things out, and continue to take down targets as they acquired them. The key ability there was the ability for them to react very quickly to a changing situation. And the biggest way they did that is they put the decision-making down to the field level. They said, you're not going to call up to the general and ask him for permission. You're going to make this happen down on the field. We're going to trust the field commanders that have the information. The other thing, too, that they did there that was super fascinating is they actually took different special forces teams and embedded people in other teams. They took an Army Ranger and they said, you're going to go sit and work with the SEALs for 6 months. And at first, one of my favorite anecdotes in this is, at first, they don't want to go there, right? The Ranger's like, no, those are the SEALs. We're not the SEALs. We're the Rangers. We're totally different than they are. Not going to happen. And then they're like, no, you're going to do it. So you have a choice. You send your worst person and you look like idiots, or you send your best person and you look like heroes. Guess what happens? They send their best guy. The best guy of the Rangers goes over to the SEALs, and the SEALs sit down and is like, this guy actually knows his shit. He knows what he's doing over here. We can go ahead and trust these guys in the field. So when the Rangers call us next time and say, hey, we need your help, or we have this thing, we can trust the system. We can trust the people, right? We do this with DevOps all the time, right? This is all about the idea of creating cross-functional teams, building connections, making sure we all talk to each other. I mentioned the Toyota Production System. The goal is the kind of the original book behind Phoenix Project. It's a great book to read. Gives a very clear kind of business and manufacturing example of the same stuff. Obviously, agile software delivery, continuous delivery, all those things. Another great book along these lines is Black Box Thinking. I read recently this fall, and it talks about the black box failure inspection of airlines, particularly compared against a lot of the medical field. A lot of the medical field has a situation where experts are considered basically gods, and their ego is untouchable. And to question them, question that they could have made a mistake of any sort, is unfathomable within the field. And as a result, there's a lot of medical errors that go uncaught because nobody's looking at the failure, right? And we see this in DevOps with blameless postmortems. We see this with the way kind of we operate, observing failure, running those types of things. So again, these are the same principles between military and special forces, between the medical field, between the airline field, between manufacturing, and what we do in DevOps and in automation. It's nothing particularly scary or new. It's just a particular application of that methodology of push the decision making down to the field, make sure you inspect and introspect your mistakes, don't cast blame. It's not an operator problem. So again, command and control structure is too slow, and one of the key things that we focus on is the minimum viable product. Short sprints, and you want to be outcome and business oriented. If the work you're doing on a team, you don't know how it aligns to how the business either makes more money, saves money, or reduces its risk, then the work is probably not valuable, or you're missing some context to why it's valuable, right? These pieces of context allow us to make appropriate decisions. One of the key things that we see a lot with our, both with our customers and even internally at Chef is when we give our engineers context to the problem, we say, hey, we're trying to do these things because they're helping us reduce risk, or we're trying to save money in these places. We let very smart people understand the context, and they come up with their own solutions, right? One of the things that happens a lot for us in the field is that we will go to a customer and see a problem that exists, a use case that exists, and we'll give back product feedback to our engineering teams. And one of the hardest things to do as an engineer is to not tell them how to solve the problem, right? Like what I want to do is I want to say, hey, look, here's the case of the problem. Here's the use case. Here's why the customer cares about it. Here's maybe a way that in which we could solve it. But that's one of the hardest things we had to learn as an organization is because if I show up as a customer-facing engineer and I go back to an SDE and say, hey, look, you should go solve the problem by implementing this piece of code in this way, at this particular spot, and like, could you do that yesterday? They're going to be like, no, man, screw you. Like, I haven't looked at it. I don't understand what it is. I don't understand how much the work it's going to be. I don't have any tests for it. I don't have any of that structure. But if we instead say, hey, look, I have a customer who really needs to get this data in this particular way because they use this data to make this business decision, then the engineering team and the product teams can do their jobs and say, hey, we figured out a right way to make that thing happen. So just to recap, component failure is normal in complex systems. Individual components will fail, and we will fail over time and randomly. We want to manage complexity and reduce the things that we can. We have one path to production is an easy way to manage complexity. We want to define all the interactions in code. We call this at Chef the coded enterprise. Really any sort of kind of DevOps, true CI/CD implementation is a key component here. We want to reduce our coupling. So anything that's tightly coupled is potentially prone to a catastrophic failure, so we want to make it a little bit looser. We want to make sure we codify any of those coupling moments in the first place. Focus on the output, API-oriented. Look for changes to the system state. Have observability to understand when things are changing on us. And then look for your common mode components. So test your failures. Do risk analysis on critical services. Build for resiliency. And in short, for people in process, some form of agile, lean, DevOps-ness in that particular space. I'm happy to talk more offline about the various components of that, but what I'd say in key is focus on the spirit of Agile, not the letter of the Agile, like the original Agile framework, right? Focus on the spirit of it that allows you to build these small, resilient, cross-functional teams to accomplish the right things for your organization. And with that, thank you, and I think we've got some time for some questions.